welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg, as usual, proudly powered by Research Luxembourg. And in today's episode, our guest is Professor Symeon Chatzinotas, who is the head of the Signal Processing and Communications Research Group, SIGCOM, at S&T, so the Interdisciplinary Center for Security, Reliability and Trust at the University of Luxembourg. In parallel, he is an adjunct professor in the Department of Electronic Systems at the Norwegian University of Science and Technology and a collaborating scholar of the Institute of Informatics and Telecommunications at the National Center for Scientific Research, Democritus. Today, I hope to talk with Symeon both about satellites and quantum communication. Symeon, thank you very much for coming today.
Thank you for the invitation.
You obtained a PhD in electronic engineering. And nowadays, what is it actually? Because, I'm still thinking, current and some putting two cables together. Probably that's not the case anymore.
Well, that's a good question. And I'm sure this has changed a lot since I did my studies. That was already 20 years ago. But indeed, my studies my master's was in electronic engineering. My bachelor was in electrical and computer engineering. So very often these go together or they are interchangeable depending on the focus of its university or department. If I have to characterize them as a whole, I think engineering in principle is learning about synthesis and analysis. And particularly if you go into this domain, you learn about electronic or electrical systems. Usually after you finish your basic training, you have to pick a specialization. And this specialization usually is meant to connect you to some application area. In my case, this was telecommunications, but very often you have computer systems. You have also power systems, energy, which is very important nowadays, and even some newer, flavors. Now there are even, if you like, quantum sciences and quantum engineering that comes into play. And usually this is interdisciplinary, but it also comes often from these electronic courses that you can go into this direction. So I think it's a bit difficult to define, but there's a lot of different application domains that you can go into after you finish a degree in such a university or in such a module.
And it's brilliant because then if you become a computer specialist, you actually have the energy part in mind as well, right? Because we don't tend to talk about it. We are all talking about sustainability right now. But then somehow there, this small print, there is what is the energy consumption of all the systems we have?
Exactly. And that keeps changing. I remember that 20 years back, it had already started changing because, this renewable energy sustainability is very important. So even 20 years ago, I remember that people were flocking from telecoms and computers into energy, which would be the next big thing. And I think now there is a very vibrant industry and a lot of electrical or electronic engineers contribute to that.
Okay, so now I know more or less a little bit about your background, but let's move to the group. I actually have a problem. Is it SIGCOM or SIGCOM?
Is SIGCOM, we pronounce it like that, but it comes from Signal Processing for Communications. So this was this was the first group attached to S&T because the previous head is also the director of S&T. He created the center 15 years ago and he launched this group. And I took over from Bjorn 4 years ago, if I remember correctly, as head of this group. So right now we are about 80 people to be 90 next year. And the naming comes from the fact that when we started, we were focusing very much on communications and signal processing applications on that, especially because Bjorn and myself were coming from an array processing background. This means, if I can give you an example, all the 5G antennas that you can see now on rooftops, they have an array of antennas in them. And how you process the signal to send it to our smartphones or to receive it is actually the techniques that we have been working for 30 or 40, 50 years now throughout the scientific community. However, that was a long time ago and the group now has grown a lot. So we cover many other disciplines. So essentially within S&T, and I would say even within University of Luxembourg, there are not so many other groups that are doing the same. We cover everything that has to do with communications and networking. And this is communication systems like the ones that we use on smartphones, but there are so many other flavors that I will explain later on. And Networking means when you go from something which is a device to a base station, but essentially if you move from that and you see the internet, so internet refers to networking. So it's a much larger system that you can see as a graph, right? So everything that has to do with that is handled by our group. And just to mention some of our focus areas, so satellite communications or non-terrestrial communications has been one of the main focuses of the group, mainly because we have a long-standing partnership with SES, which is a major satellite operator based in the country. And lately, we have also developed expertise on quantum communications. That was partly politically motivated, so Luxembourg is investing heavily on that. So we launched some projects, and now we are in the process of creating the national quantum network.
Okay, so a lot of networks and a lot of things that I think are very difficult to explain to the general public, because I have to say that I visited one of your labs and I was trying very hard, but it was very difficult to understand. Also because it makes me think, I think some of my listeners already know, my father was a physicist. And my mother was always laughing that he's just measuring something you can't see, because of course he was just looking at particles and, and then measuring what is the impact or whatever. So it's a bit like that. You can actually show a receiver, right? Or how the signal is sent, but then you don't see it. So how do you actually explain it to people? Like, what is happening in your work, really?
Yeah, that's a good question. Normally when we teach, apart from the theory, there is also a lab. And students have to spend time in the lab. And when we talk about radio or wireless communications, we live now at an age that you can afford to buy what we call software-defined radios. This is essentially some devices that you can program with software, and you can essentially develop, if you like, your own wireless communication system just by writing code without having to build anything else. So this is what we're using in our labs, and we are asking the students to build from basic principles their own wireless system. So without having to build any hardware or solder any cables together, they can actually understand the principles purely based on the software. And of course, at the end, they can see how they can send bits from one place to the other over the air based on what they have constructed.
And it's amazing if you think about it. I still am in the generation that remembers cables for everything, And when you said like your own network, I remember the home network we had with my father. We've gone such a long way.
Yeah, definitely. And it's a great age for experimentation, because there are so many things that you can develop from basic principles into a paper, and then you can actually demonstrate it all the way within a university without having to collaborate with the industry. And of course, that's also the new way that the industry is expecting to interface with us. So we are expected to do that. So we even have the national operators that have installed 5G base stations for us on our rooftop, and we can have our own terminals communicating with them, our own SIM cards. So it's like having our own, if you like, 5G network to play with. And it's all meant to help us demonstrate all these aspects that we are developing here.
So you mentioned two things that I want to go the direction of, but let's start with the satellite communication, because that's also one of your expertise. So I think nowadays we really know that there are quite a lot of satellites somewhere there. Okay, we don't really know exactly where, so I hope you'll tell us that in a second. But first of all, why do we have all those satellites? Do we really need them there? Could we just scrap that part? I know you can't say it because it's your research, but theoretically.
Yeah, no, it's something that I believe we cannot live without anymore. More importantly, it has become a sovereign asset now. To give you one of the most solid examples, we're all used to GPS, right? GPS is based on signals that come from the sky, and GPS is an American system, right? It was built by the US, it's operated by the US. And of course, as soon as it became popular, the rest of the world realized that we cannot have someone switching it off. So now there is the Chinese version, there is the European version, Galileo and so on. There's the Russian version, the Japanese version. So more or less, everyone is trying to have their own positioning system because they understood how important it is now to everyday life. Similar things happen with other areas where you have satellites for. So maybe positioning is the one that everyone knows about. I think the next one that probably people have used on a daily basis is Earth observation. So everybody goes on Google Maps or some relevant platform. So all the pictures that we see there come from satellites that observe the Earth. So these are visual pictures, of course, but there are other frequencies or other kind of Earth observation that we do when we want to observe phenomena that are not going through the visual frequency that we can see as humans, right? So this is a whole area of Earth observation, and I'm sure there are colleagues at least that they can speak about this much better than I do. So our area here is mainly focused on communications. So we do a bit of positioning, but we mainly do the communications part. And usually this is what people have not used so much. So you have used communications over satellites if you have connected to the internet while you were flying, while you were on a ship in the middle of nowhere.
Or on a ferry, right?
On a ferry, yeah. Or if you decided to buy a satellite terminal because you live in the countryside and you don't get decent DSL connections or 5G connections for that matter. However, this is one of the most, I would say, rapidly developing areas because this is a big part of what 6G is promising. So the next generation is promising that you can get signal anywhere. And this means that we're not interested only to cover the urban areas, and we want to have technologies that can reach the entire Earth. So one of the most important areas that we work on is called non-terrestrial networks, and it's meant to do exactly that. It's meant to create satellite systems, specifically, that can provide 6G connectivity directly through the smartphones even that we're using today. To be honest, it's also the fastest growing source of satellites at the moment. So most of the satellites that fly today coming mainly from these large LEO constellations like Starlink from SpaceX. You might have heard about that.
Of course, I was just wondering, 15 minutes until we mentioned Starlink.
So there are other competitors, but people usually refer to that because they are the most advanced one. So they are responsible for a lot of the satellites, and I don't want to ruin the answer to my quiz question.
Exactly. So don't ruin it. And
Yes.
this is exactly the moment when I will ask you to ask it. So your listeners, remember, always in the podcast, we have this moment when I ask my guests to ask the pub quiz question, and the answer is only at the end. So I'll be controlling that Symeon doesn't reveal the answer until the end of the podcast, although I had guests that revealed it earlier. So maybe just listen very carefully. Maybe it will be somewhere there. So Symeon, can you please ask the question and remember, answer only at the end?
Yes, so the question is, how many of you know how many satellites we have flying today and how many we had a couple of years ago, just to understand how quickly this is growing?
And with satellites, we mean what exactly? CubeSat as well, flying somewhere there, or not really?
Normally, CubeSats are something particular. Usually they have very short lifetime. I'm not sure if they're being taken into account in the statistics, but usually whatever flies, I would say in microsatellite and above, so it's not a shoe size, but you have a certain volume and mass, then this is counted in the statistics, and there are even systems that are monitoring the orbits of all the satellites flying around us because of potential collisions, right?
Yes.
So I think these are the statistics that we have in general available, and these are the satellites that I refer to.
So remember, answer only at the end, unless we happen to just find the minefield and reveal it earlier, but I'll try not to do that. Okay, so we said satellites, so we just already have this idea, okay, the weight and the size and whatever, but then where are they? What's the distance, let's say, from here at S&T, because we were recording it at S&T, to the next satellite? Are they all at the same orbit, or are there different orbits for different satellites?
That's a very good question. So maybe it will give me also the chance to explain what's the latest trends and technologies. So traditionally, satellites were deployed at 38,000 kilometers from us.
Why 38?
It's exact because if you put a satellite in that orbit and it's around the equator and it can turn exactly at the same rotation speed as the Earth, then it's also a very important problem that the satellite will be always at the same point in the sky when you look from a particular point in Earth. Why this is important? Because you usually have to point to it. You have to set up an antenna. So the signals are very weak. So you have to set up a sizable antenna, nothing like the antennas that we have in our smartphones, to be able to send and receive signals. So if this point in the sky is not moving, it's in geo orbit, as we say, then it solves this particular problem. Then the next step that happened a few years back, I want to say maybe maximum 10 years back, it was the medium Earth orbit. So this is something in the neighborhood of 8,000 kilometers. And again, this was something novel, something that happened for the first time. And we're lucky that the company that is actually acquired and operating this system, the only communication MEO system in the world, is here in the country, right? So this has also some advantages because essentially you still see a very large part of the Earth from 8,000 kilometers. But of course, you are no longer geosynchronous. It means that the satellites are moving. Usually it takes about 6 hours that we see them, and then we no longer see them. And we need the antennas to track them if we want to communicate. And of course, as we mentioned already, the largest, I would say, hype and also scientific, I would say, trend nowadays, it is large LEO constellation that now they come by the dozen. Everybody wants to have one. The usual question that the audience asks is, why do we do this now? Why didn't we do this earlier? And the question is that we tried to do this earlier. A couple of decades ago, there were a lot of initiatives to have these large LEO constellations which can fly as close as to 500 kilometers up to, I would say, 1,200 kilometers. And they all went bankrupt. Yeah. So the only one that survived was the ones that were acquired by certain, I would say, defense ministry and so on. But they couldn't survive based on the demand that we have from everyday users. What's different now is that we have the technology to deploy them in mass in a way that there might be a commercial business out of it. Because you need that if the companies are to survive and keep this operation running without the help from the state, right? And this is what all these different initiatives are trying to do at the moment.
And also the fact that we are using internet as such, right? And we need that connectivity.
Exactly. And I think many countries realized that internet now is something crucial for the citizen. It's as important as water, is as important as electricity, right? So that's why they have large funding schemes to promise a minimum amount of broadband coverage no matter where you are in the country. I mean, we don't have this problem in Luxembourg, obviously, but you can imagine countries that most of it's either in mountains, rural, deserts. And these are the countries that essentially have this particular issue. And I think the other part of the innovation is now that, again, with all these large LEO constellations, you can have a terminal that you can go and buy yourself or order online. It comes to your place and you can install it yourself without the need of a technical expert. And I think this is what created this whole renaissance, if you like, of large LEO constellations. And that's why they're highly popular at the moment.
So you say terminal. So what does a terminal let us do actually?
So usually, I'll talk again about these large LEO constellations. The latest terminals that you can buy, they come in a box. It's essentially an antenna that has inside an array. When I talk about an array, it's that is not a single antenna, but many smaller antennas that are coordinated. So usually you have what we call electromechanical steering. So you have to follow a satellite which goes across the sky. Part of it is being done by the antenna moving, the actual antenna moving, but a big part of it is done by things that you cannot see. And these are the beams that are created by these small antennas that you have in there. Apart from that, especially in these latest developments that you can buy, there's just a cable to a modem that is very similar to the DSL modem that you have in your house, and you connect to it through Wi-Fi, and you have internet. It's as simple as that. The only condition is that you have to be able to look at the sky, of course.
Of course. And then also, I guess you have to have some kind of an agreement with the satellite owner that is giving you the signal or not.
Exactly. So this is all straightforward in a way that most of the companies that offer such services, it comes with a subscription-based model. So the same way that you get internet from your DSL provider, you can get it from such companies. And as I said, this is not something that happened. You could do this already maybe 20, 30 years back. The difference was that now it's much easier without needing some expert or technician to come to your house. And that's why there is, I would say, massive adoption, especially for people that cannot really get decent connectivity from landlines.
Okay, so we're talking still about a terminal, but you said the future would be we could have it anywhere on our phones, in our cars. So what is it here? Miniaturization we're talking about, or new technologies that will let us get the signal?
Yeah, so this is one of the most challenging, I would say, scientific problems nowadays, is the most active one as well, is whether we can use our 5G smartphones or 6G in the future to connect directly to satellites. That would solve a lot of problems, mainly because everyone has one of those in their pocket. And it's beneficial both for the consumer of the service, because you might be stranded somewhere and you don't have access to the normal terrestrial network. And also it's very beneficial for the companies that are building the systems, because they immediately have access to a very large population. Now, the state of the art is that you can connect through your smartphone. There are a few smartphones. Apple started this trend. Now I think Huawei, Samsung, most of the companies, they're following this trend. But there is a catch. Actually, there are two catches. The first one is that the technology is not good enough to get any service that is comparable to what we used to. So we're talking about really basic service now, which is sending some messages. Best case scenario, maybe opening some web pages, but no video calls, no really any kind of high volume content. The second catch is that we all have a smartphone in our pocket. Why? Because they all follow the same standard. And we want to have the same standard because we want to use it in the next country that we travel to. But this is not the way it's happening right now with smartphone, direct to smartphone connectivity from the satellite. So many of these companies, they're developing their own technologies, their own standards. And we as scientists, we're trying to essentially create something will be accepted by everyone. And this is very important because as a consumers, it's in our benefit to be able to connect to any satellite that flies there, no matter if it's the one that has a deal with Apple or Samsung or Huawei, right? So
unless you have
important.
like 5 phones in your pocket and then
Exactly.
You just take out the right one.
Exactly. So we're not there yet, but there is, I think the scientific community is putting a lot of weight, and hopefully this is where this technology is going.
Wait, let me understand this. So why are we looking into 6G? Shouldn't we just be looking at the satellite communication and just drop the whole 6G trend?
Yeah, so I think 6G comes from the fact that usually there is a very long and tenuous process of coming up with the standards that our smartphones follow. We know them as generations, 1G, 2G, up to 5G nowadays. But behind it, there's a huge amount of people that have to agree on things so that the companies that build the equipment, they can talk to each other. So, for example, if I buy a smartphone from Nokia, it should be able to talk to a base station from Ericsson, right? So that's the most important reason that we want to comply to standardization. Now, going back to your question, the problem is that 5G is already out there, and these satellite communications or non-terrestrial networks, they were not ready when the 5G base station started to roll out. So now we're trying to make them ready for the next generation, also to give time so that potential satellites might incorporate this technology. So in the future, we'd like to see maybe entire base stations that fly on satellites. And one of the, I would say, most important technological enablers is to have very large antennas flying in the sky so that we can get better quality of experience than messaging. And there are companies that are working in that direction. And to give you an example, there is a company that managed to fly and deploy an antenna which is equivalent to 64 square meters. And this is something that flies very folded, as you understand, and then it deploys and it creates something that can pick really weak signals or send strong signals to the ground.
Okay, so there is a lot coming, as I understand. But I was also thinking that, we're talking all satellites. Okay, we understand a bit more, I hope, after our discussion. But the traditional way we as a general public would use satellites that we are not discussing that much anymore is just satellite TV. So what is happening with that?
Yeah, so I would say that's the largest threat in the established ecosystem, because a lot of the established companies, they made a lot of business based on TV or radio broadcasting. And now with the over-the-top services like Netflix, Amazon, and so on, then this revenue is declining. So people, they call it cord cutting, right? This applies not only to broadcasting TV over satellites, but even over coaxial cables, which are the cables that come into our homes, right? So in general, there is this cord cutting trend, which is very dangerous because it means that all these companies, they have to somehow reinvent themselves. They have to switch from broadcasting content to really content on demand. I think it's still quite popular. There's still quite a lot of revenue that is being made, but it keeps declining. So I think it's a period that you have to adapt or perish. And to adapt, you have to really embrace all these technological challenges, even the non-geostationary MEO and LEO satellites, to be able to be competitive in this new world.
And is it possible to just change the way the satellite is used? So let's say those satellites that are used for radio, TV broadcasting can be used for, future connectivity?
Yeah, so this is already something that was done as a first step. So in principle, you can provide internet from the similar satellites or similar orbits that you would do for TV broadcasting. The difference is that for TV broadcasting, we always used the geosynchronous constellations. That was for the simple manner that we didn't want to have very expensive equipment that tracks the satellites. And now the first step that was done is to go from broadcasting TV to broadcasting internet. And you can still do that. And there are a lot of satellites that do that nowadays. But the problem is that this cannot scale very well if there is a lot of demand. Why? Because you're very, very far away. You're 38,000 kilometers. So these are one of the most advanced satellites that you're using for broadband communications from GEO. But still, due to the physics of the problem, due to the fact that you're so far away, the signals are very weak and there is also a lot of delay. And delay is problematic for a lot of applications that we take for granted. So teleconferences, gaming, all these require to have a small delay in your communication. Otherwise, the quality of experience is very bad.
Yes, of course. And, if we're talking about autonomous driving as well, that we're supposed to use the communication for, then, we have a problem.
Exactly.
Maybe if all the cars are on the same frequency, then maybe everyone will be moving slow. I don't know, then that's okay. But everyone gets used to the delay, but most probably we have to find a different solution there.
Yeah. No, I think going back to the automotive, if you like, industry, it's highly probable that in the future, different vehicles would be equipped with a very flat and small antenna that you can already incorporate it even when you produce the vehicles. And then you could actually get maps or content or even broadcasting information. But I think that the critical applications that have to do, for example, with pedestrian detection, obstacle detection, platooning. You might have other cases where you want to coordinate who goes first, crossroad. So all these things, they are somehow delay sensitive. So all the delay sensitive applications for these, I want to say, semi-autonomous vehicles, they would be going actually through the terrestrial networks. Because of the latency that you have, even to reach the LEO, it's still considerable compared to what you would get through your terrestrial base stations.
And I assume it's basic physics, right? So it's nothing we can do, because we talk a lot about delay also when it comes to communications when we go to the moon or further. There are no technologies we can have that will deal with this.
There's nothing we can do about this. The most, I would say, scientific solution to this problem is that sometimes you can have intelligence which is embedded in the vehicle, and then it's assisted by some communication. Right? But if you base it only on the communication, that's why I said semi-autonomous, then this delay becomes very problematic. And, very well you mentioned this problem of going even to deep space. Then sometimes you have to wait like minutes so that the signal reaches. So this is purely the speed of light, there's nothing that we can do about this.
Okay, pity, because, I am very much interested in space applications, and I was just wondering, can we solve it? But yes, this is the moment when we reach the wall and we have to figure out something else.
Yeah, well, I can give you an example if you like. So we're actually dealing with this problem of controlling lunar rovers, let's say, on the moon. Luxembourg is big on space mining, so this is something that could happen in the future. One of the first applications would be collecting rocks that contain water, right? And of course, there won't be any humans around. It's going to be just robots, and we have to control them all the way from the Earth. So normally how we do that is that, again, it's the same solution. There is some intelligence which is either on a moon village that we have very close to the rovers, or on a satellite which orbits the moon. So then this intelligence can really guide with reasonable latency without having to go all the way back to the Earth.
And that's basically the future of ISS, isn't it? The whole idea of orbiting the moon.
Exactly. So, I mean, there are big plans for going back to the moon. You might have heard about this Artemis initiative. So it's highly probable that we're going to have humans also back on the moon. But I think the most important, which is not very often advertised, is that we want to have infrastructure. And infrastructure means that you want to have constellations of satellites orbiting the moon. And you want to provide similar services as we have in Earth. So positioning, communications, observation. The difference is that there will be nothing on the ground. Here we have everything on the ground, and we want to go to space. As we approach now this kind of moon village initiative, then we have to work the other way around, which is much more challenging.
Of course, there are loads of challenges there. But what is also challenging is the second topic I wanted to move to, so the quantum communications. So we have this buzzword quantum. And I think sometimes when people hear it, they cringe because they think like, oh God, this is something very difficult to explain. So what was the easiest way you can explain to us what is a quantum computer and quantum communications?
Good. So I'll give it my best. So first of all, what is quantum? So when I try to explain quantum, let's say to our students that have not heard anything about this, I try to explain it in the contradiction between macroscopic and microscopic events. So you can have physical phenomena that if you look at them from a macroscopic perspective, they behave a certain way. If you look at it from another perspective, microscopic, then they behave completely differently. So quantum actually focuses on the microscopic aspects. It focuses on the smallest particles that we can observe and how they behave. And this is very different from looking at these particles in a massive scale that they can behave, for example, like wave functions. So when we look at them as particles, they usually comply to the quantum mechanics. And this is an area of very high interest. It's actually one of the areas that the different sovereign countries compete for supremacy because it has a lot of applications. Right? It's not only quantum communications, it's not only quantum computing, there is also quantum sensing, which is essentially how you build better sensors based on these principles. And in general, if you are able to manipulate this microscopic aspect of nature, in general, you can achieve better performance, whether this is accuracy, whether this is security, communication, and so on. So, of course, we don't do all that. Here at the group, we focus on a particular area. We focus on quantum communications. The long-term vision of quantum communications is the quantum internet. This means that in a probable future, on top of our traditional networks that we have today, which actually exchange bits, we'll be able to exchange qubits, which is quantum bits, and they're not going to be processed by digital computers, they're going to be processed by quantum computers. So what this offers us, actually the main rationale behind it is because the quantum computers scale in terms of what they can do much more quickly than the classical computers. So if you increase using the same rate the bits and the qubits, the quantum computers can solve much more complicated problems. And this is actually the source of one of the problems that led us to get involved in quantum communications, which is the fact that there is a threat that this varies depending on who you ask, but I would say 10 to 30 years from now, there are going to be quantum computers which are capable enough to break the cryptographic protocols that we use today. And this is something that we use multiple times, every day, everyone across the world. Of course, maybe we're not concerned about our information. Maybe it's not critical enough. But this is also used for information which is highly critical, whether this is in terms of national security, in terms of privacy of health data, privacy of financial data, and so on. So I'll stop there. Maybe you can ask me a question because I don't want to turn this into a monologue.
No, it's great. I'm, of course, trying to grasp it all. And I'm just wondering, how do you get access to that microscopic part? Because it's not with a microscope, obviously.
Exactly. So, as I said, quantum effects can appear in any kind of particles. But one of the most important particles that we use very often and we know how to manipulate is the photons. So photons are being used every day when we have fiber optics. And now we know that sometimes we have fiber optics coming all the way to our houses, right? In the past, it used to be just to connect data centers, but now it goes all the way to our outlet. So we have a long experience on how to manipulate these photons. But what changes when you go to quantum is that you have to be able to manipulate single photons. And this is not what we do today. Today, usually there is a bunch of photons, we call them a pulse, which is transmitted. And then we can, for example, detect the presence or the absence of this pulse. And this is one of the simplest way to communicate. But now the scientists, and especially physicists, engineers, also cryptanalysts, they're trying to use the smallest particle that we can manipulate within these optical fibers, which is the photon, encode information on the photon. Now, there are, I would say, maybe 2 or 3 important differences that if somebody wants to remember something, this is what they should. And this is the difference between bits and qubits. So we actually want to turn photons into qubits. We want to imprint quantum information on the photons. And why this is so challenging? It's so challenging because we cannot read the information that we imprinted on a photon without destroying it, right? So imagine that this is the most basic principle is that you can reproduce the information. You can store it, you can read it, and then you can read it again, or you can create a copy of it. All that, it's impossible in the quantum world. Because once you read it, you actually destroyed what you have read. And that's why there is a complete whole new science. And that's why, going back to the first question, I said that now engineers that go to school today, they probably have to study quantum mechanics. We didn't have to do that 20 years ago. But now we're actually teaching that because it's a very important knowledge for the future technologies.
So the problem is of not knowing what to do so we don't destroy it? Or is it the problem of actually having somewhere a copy before it gets destroyed?
The problem is that this is one of the basic, if you like, principles of quantum mechanics, that you cannot measure something without changing it, right? So as soon as you measure something, you essentially change it. And this doesn't happen with our current bits. We can measure them 0 or 1, it will still stay 0 or 1. And that's why everything has to be rethought. I mean, really from how you create the qubits, how you communicate the qubits, how you read the information, how you create quantum memories, which is one of the things that are one of the most important bottlenecks today. So we don't have quantum memories. So we cannot retain the information that we have in a qubit for more than 6 hours. That's the state of the art today. So things that we take as given, so we have like terabytes of storage on our mobile phones. In quantum, they are really in I would say, very elementary form.
But once you crack it,
yes,
the satisfaction is immense.
Exactly. Just to be precise, these are kind of fundamental problems that they're very much studied by physicists. In the group, we are communication engineers. So essentially, how we work is that we're trying to be able to take the advances that the physicists are producing and to show how you can apply them in the real world. So just to give you some information of what we are currently doing, maybe that's of interest to the audience. is that we are taking the first steps to create a national Luxembourgese quantum communication infrastructure. This will have a few nodes spread across the country, connected with fiber optics. And we want, as a first proof of concept, to show that you can use this platform to securely exchange keys. And these keys are used then to encrypt the information that we want to communicate through our conventional networks. And the principle exactly that this is based on is the principle that I mentioned before. So if we send a qubit over a fiber line and we have a malicious entity that wants to read it, they will destroy this information. Then once they destroy it, we can detect that it was destroyed at the other end. We know that something happened in the meantime. Then we know that we have been compromised. That's why it's considered one of the most secure ways of really exchanging this kind of cryptographic keys among two locations.
But as you said, it's a race against time to be first, because otherwise, if it's used to produce threats, then we have a very serious problem.
Yes, indeed. And unfortunately, we're not first. So, there are countries that are more advanced in that respect, but I think Europe is catching up quite quickly. There is a huge initiative from the European Commission called EuroQCI, and this is meant to create in the next 2 years one of these national quantum infrastructures for communication in every member state. The next step is to interconnect them across borders, and this can be done whether you install fiber links that cross the borders or even through satellites. So that's why we're also interested in that.
Okay.
Because one of the limitations is that you cannot send photons very far away and you cannot amplify them. So usually now we know that we have fiber optic cables that run under the Atlantic Ocean, under even the Pacific Ocean, right? This is mainly because we can amplify again and again, and this amplification happens at the bottom of the sea. Now, the problem with these quantum links is that you cannot amplify the information because that means reading or disturbing the information. So that's why at the moment we have limitations. We can go as far as 200 kilometers away if we're lucky.
That's good for Luxembourg.
That's good for Luxembourg. Don't need more. But if we want to communicate to Ireland or to Greece without going through a bunch of other countries in between, that's why we need the satellites. And now there is an initiative to create a satellite which is specifically meant to create this exchange of keys. And major difference is that it works again with optical communications. That means lasers, not radio frequencies as we use in our mobile phones, but lasers.
That's what I was thinking, because how do you send those photons? I mean, it has to be a different type of way of doing it.
Yeah. So mainly if you want to go over the air, you have to use lasers. But again, these are very weak lasers because we're talking about sending very weak photons. So you don't
see the beam?
No. You don't see the beam because it's not in the visible light. Most importantly, most of the experiments happen during night because the sun is sending photons. A lot of other things around us send photons. So when it's dark, the noise around us is much lower. So it's much easier for us to send photons back and forth over the air.
Okay, so this gives us a great background. And in case you're wondering what happens at night, some people might be up to some really no good, but some people are just sending beams of photons somewhere.
Exactly.
Okay, well, it all depends on what you like doing at night. Fair enough. I would love to ask you more questions, but I think this means we have to meet again once the center is more developed and you can tell us more. But we have to now wrap up, which means solving the pub quiz question. And we managed not to give the answer to the audience, so I'm very happy. So once again, if you can remind us what the question was about and then give us the answer.
Great. So the question was, how many satellites were flying a couple of years ago and how many satellites we have flying today?
Around the Earth.
Around the Earth. That's true. Because we have satellites that even went beyond our solar system now. So let's make it specific, around the Earth. And these are very kind of rough orders that I will give you, but they will make you appreciate how quickly this is developing. So from some statistics over public sources on the internet, and you can even look it up yourselves, we had about 1,000 satellites in 22. And now entering to 24, there are, I would say, launches that are happening maybe 4-5 times a month each launch carrying maybe up to 60, 70 satellites. So this is mainly, again, from these large LEO constellations that they are creating this huge crowded environment in space. Rough estimates, I think we're in the tens of thousands now. And it will keep growing. And again, this creates a very big challenge for the community. And this is the space debris. So I think a few days back, the European Space Agency issued a charter specifically for that reason, that there has to be a sustainable way of not only putting assets in the sky, but also decommissioning them, because there is a real threat that once you have a collision, then this will create a chain reaction, and then that would be catastrophic for our communications. There's no way to recover. There's no way to, let's say, collect all this garbage after such a chain reaction. So I think the humanity is aware of this, and we're making shy steps in this direction. But it's one of the major challenges that we'll have to solve in the next few years.
So quite a few challenges to think about, but for sure space debris is something we need to discuss. And I did discuss it a few times already, so we'll come back to it. And hopefully the plans for deorbiting all those satellites are going to get more improved, let's put it this way, than They are right now. Thank you, Symeon, very much for telling us all about the satellites and quantum communications as well. It was a pleasure to have you here today.
Thank you very much, Hannah, for the opportunity.
And this is it for today. Don't forget to subscribe, to follow us, to check what we are writing on all the social media, and of course, to suggest guests or just comment on whatever we are talking about. This was Silax, and my name is Hanna Siemaszko.